Now see, we are starting today, we are still on electronic conductor. So in an electronic conductor, the conduction takes place because of movement of electrons. Conduction takes place because of movement of electrons. It is clear. Now why does so even though the electrons are moving, they are mobile electrons, what happens? When the electrons are moving, they hit against the atom of the metal, and that is the concept of resistance. That is the concept of resistance. It is clear. So according to Ohm's law, V is equal to IR, where V is the potential difference, I is the current, and R is the resistance. Okay. Now R, the resistance, is equal to rho into L upon A, where rho is called as resistivity. Sometimes in physics they call it as specific resistance. What do you mean by resistivity or specific resistance? The resistance offered by a conductor when the length is 1 meter and area of cross section is 1 meter square. It is clear. But in the common situation, we always talk of length is 1 centimeter and area is 1 centimeter square. It is clear. Now resistance is measured in the unit of ohms. Now what happens is, if I find the reciprocal of this, 1 upon R, the reciprocal of resistance is G. G is called as conductance. And that is equal to what? 1 upon rho into A by L. Now 1 upon rho, see, this is called as conductance, this is called as conductivity. So what is the equation you are getting for an electronic conductor? You get G. G is the conductance, which is the reciprocal of resistance, and that is equal to K. What is K? K is called conductivity into A by L. So what does your conductivity become? Conductivity becomes G, the conductance, into L upon A. So this is one equation you have got. What is the other equation you have got? K is also equal to 1 upon R into L upon A. So 1 upon R is what? Is per ohm. Resistance is ohm. So 1 upon R is per ohm. And then look, this is length is in centimeter, this is centimeter square, per ohm per centimeter. But per ohm is also called as Siemens, capital S. Small s is second, so this is capital S. So Siemens per centimeter is a unit of conductivity. So having derived this, now we have to talk about what you call in an electrolytic solution. Now in an electrolytic solution, the situation is very different here because concentration plays a part. So first of all, in an electrolytic conductor, let us start with that point and then go ahead. Now in an electrolytic conductor, what happens is the conduction is because of movement of ions. Conduction is because of movement of ions. Is this clear? So concentration of the ions in the solution play a very important part. So here what I can say, the conductance, no, then we call it as molar conductance. We just don't say G. We don't say G. We say molar conductance. Molar conductance is equal to conductivity K upon concentration. So here, so what do we get? Now you have to understand that as concentration decreases, now understand, concentration decreases, what is going to happen? More and more and more of ions is going to dissociate, because we have this in ionic equilibria. What is it that we have in ionic equilibria? That alpha, the degree of dissociation is inversely proportional to square root of concentration. So as concentration decreases, degree of dissociation increases. So that is the logic we are applying over here. What are we applying? We are saying that as concentration decreases, molar conductivity increases. Molar conductivity increases mainly because the dissociation increases, availability of ions increases, so automatically the molar conductance increases. Okay. But now what happens is, look, now we have to simplify this equation. See, concentration unit was moles per 1000 ml, moles per liter. So C is the concentration, okay, when the volume is 1000 ml. Okay, no, when it is 1 molar, when the concentration is 1 molar, the volume of the solution is 1000 ml. But here we are taking concentration C molar in a volume V ml. Then what is the relationship we get for C? Now try to understand in mathematics, concentration and volume are inversely proportional. So when they are inversely proportional, you can't do cross multiplication. What do you get? 1000, then in this 1000 into 1 will be V into C. So your C, the concentration now becomes 1000 upon, or V. This is V. So what happens is your V will be equal to, okay, your V will be equal to what? 1000 upon C. So whatever volume you take, so now we get a new equation, kappa. This term is called kappa. It is not lambda. Kappa M is what? It is molar conductance or molar conductance. So molar conductance will have, so this will be equal to what? We substitute 1000 into K by C. 1000 into K by C. Okay. Now, this was one equation that we got. Okay. Now, I'll rub this talking about variation of conductivity. So, your conductivity is K with concentration. So therefore what happens? First we have to define what is conductivity. Definition of conductivity is it is the conduction in unit volume of solution. Conduction in unit volume of solution. That is K. In unit, it is C. Unit volume. Molar conductivity is when something molar is there. When the volume becomes 1 centimeter cube, whatever is the conductance, that will be called as conductivity. So we have connection from there. See, what is it that we are doing? We are taking a beaker. And placing 2 platinum rods. The area of the platinum surface is 1 centimeter square and the distance between them is 1 centimeter. So between them whatever volume is there, that will be unit volume, because it is 1 centimeter square into centimeters. So this volume will be 1 centimeter cube. So conduction of in unit volume of solution is what we call as is conductivity. In case of solution, the definition there will be different. For electrolytic conductor, definition in a electrolytic solution will be slightly different. Now what happens is, now look at the case of, look at this. In case of conductivity K, as the dilution increases, that is concentration decreases. As you dilute, as you add more volume, look at the contradiction that you will come across. And this is a question which they ask. What happens as the concentration decreases? That means you are adding more and more and more water. The number of ions present in this unit volume decreases. So conductivity decreases. Is this clear? Concentration decreases. Sorry, first we'll talk about concentration decreases, conductivity decreases. So understand these two sentences. Very frequently interchanged and asked. So when we come to molar conductivity, so in case of molar conductivity, as concentration decreases, more and more of the electrolyte is dissociating, more and more of the electrolyte is dissociating, so the molar conductivity increases. That is the logic. Okay. But here, conductivity is in unit volume. As you go on adding water, that means concentration is decreasing, dilution is increasing, number of ions per unit ml is decreasing, so conductivity also decreases. Conductivity also decreases. Is this clear? So these are two steps. So always understand in the entrance exam, are they talking about molar conductance or are they talking about conductivity? Molar conductance, dilution, more dissociation, more ions, more conductivity. Is this clear? More is a molar conductance. Here, conductivity is per unit volume. As you dilute, number of ions per unit ml decreases, conductivity decreases. Because conductivity is molar conductance per unit volume. Is this clear? So these are two things that I have discussed. Now we have to discuss the activity. Variation of molar conductivity with, I am looking for the foot ruler, the graph. Yeah. Variation of molar conductivity with concentration. See, what happened was that when a graph of molar conductivity, kappa m, it's not lambda m, it's kappa m, was plotted against square root of concentration. Why square root of concentration? Because degree of dissociation is inversely proportional to square root of concentration. As concentration increases, the value of ions will. So now what is going to happen? What did we tell? See, as concentration increases, what is going to happen? More ions, more forces of attraction, means less ions are available, molar conductivity will decrease. So look, so as concentration decreases, now look at the other sentence. As concentration decreases, what happens? Dilution increases, correct? Concentration and dilution are inversely. Dilution increases. And haven't we said alpha is directly proportional to square root of dilution? That means alpha, the degree of dissociation is going to increase. More and more ions will be available. So now in a strong electrolyte, what am I doing? Just imagine. Initially, this is concentration increasing. So this was one plot. I decrease the concentration. I am going like this. So what is going to happen? I decrease the concentration, and what happens? The molar conductivity increases. Why does the molar conductivity increases? Because alpha increases, more dissociation. Then we have one more. So now when I join these three lines, what happens? You are going on decreasing the concentration. What is this? This is supposed to be zero concentration. So there cannot be anything called as zero concentration. This is called as position of infinite dilution. So now if I have to find out what is the molar conductance at infinite dilution. What is infinite dilution? I take 1 molar solution, sodium chloride, and put it in Powai lake. I put it in the lake. Millions and millions of gallons of water is there. That is infinite dilution. Is this clear? But you can't get the molar conductance at that situation. So what we will do over here is, we'll take this graph and simply extrapolate it on the y-axis. So when I extrapolate this on the y-axis, this value is kappa naught. Kappa naught is what? It is molar conductance. It is molar conductance at infinite dilution. Molar conductance at infinite dilution. Very important. Now what is the next thing? So this was a graph for what? This was a graph for strong electrolyte. This was a graph for a strong electrolyte. Now what happens for a weak electrolyte? For a weak electrolyte, as you go on decreasing the concentration, increasing the volume, it comes like this. Now in this curve, so this is the story of a weak electrolyte. So in this case it comes closer and closer and closer, but will not meet the y-axis. So you cannot easily find out the molar conductance at infinite dilution for a weak electrolyte. We have to use a indirect method. Is this point clear? Whereas for a strong electrolyte, just extrapolation of the curve is easy. So based on this, what happened was the graph. See, this is a graph of the type y is equal to mx plus c. Please remember, mathematics. This is a straight line with a y-intercept. Y is equal to mx plus c. So what happens? Your y is molar conductance. What is mx? Mx is a root c. Y is equal to mx, a root c. And then what do you have? Y-intercept. Your y-intercept happens to be what? Your y-intercept happens to be molar conductance at infinite dilution. So what can I have? I have therefore a equation. If I keep this and take this over here, I get a equation. Molar conductance at infinite dilution will be molar conductance minus a root c. So this is one Kohlrausch-Gibbs equation. This is called as Kohlrausch-Gibbs equation. So understand, we got this from the plot. Y is equal to mx plus c, and we simply rearrange that. That's why we got minus a by a root c. Is this point clear? Now this was about conduction, okay? Now we come to next one is Kohlrock's law of independent migration of ions. And then we are going to connect all this now. Means tomorrow, even if you become a doctor, you will have to do all this, because these things are going to become very common now in the world. I don't know about India. So now we have, listen, we have the Kohlrock law of independent migration of ions. Very important. The statement has to be as per the textbook, because I'll tell you where the mistake is made. Even the textbook I made, I have underlined it. He says, or the law states, that this word is very important: at infinite dilution. At infinite dilution. If you miss this word, at infinite dilution, you are straight away given 0 mark in the board. Absolutely, there is no mercy on this. That at infinite dilution, so this word very, very important. What is going to happen at infinite dilution? Each ion at infinite dilution, each ion migrates independently of its co-ion and makes its own contribution to the total molar conductivity of an electrolyte. Last statement is of no consequence. Irrespective of the nature of other ion. Irrespective of the nature of the other ion. So now your molar conductivity at infinite dilution, is this clear? Will be the sum of the conductivity at infinite dilution of the cation and the sum of the anion. So try to understand what I have done. While writing, this was kappa and this is lambda. Molar conductivity at infinite dilution for individual ions are represented as lambda naught. For the salt it will be, for the electrolyte it will be kappa. What am I trying to tell you? I told you, molar conductivity at infinite dilution is very difficult to detect. Kohlrock has solved our problem. What did Kohlrock say? Look, suppose if you have barium chloride. So what is the molar conductivity of barium chloride at infinite dilution? We have standard values. Just find out the value of molar conductivity of barium ion at infinite dilution plus 2 times, because there are two chloride ions, no? Independent of each ion. Each one is going to, if there are two ions, each is going to contribute, each is going to contribute to the molar conductivity. So what do we have now? 2 into molar conductivity at infinite dilution of chloride ion. Now these values are known to us. Is this clear? Just substitute, you will get the molar conductivity. So we come to what is the application of Kohlrausch law. Application of what? The Kohlrausch law. See, it's Kohlrausch. Indians pronounce it Kohlrausch. If you look at German, it's Kohlrausch. Application of Kohlrausch law. What is the application? The first application is in finding the molar conductivity at infinite dilution of a weak electrolyte. I told you, from the graph we can't calculate. I'll give you an example. Suppose I want to find out the molar conductivity of acetic acid, a weak acid, at infinite dilution. What will I do? This value, I just put 3 values. I'll find out the molar conductivity of HCl at infinite dilution. Then I'll find out the molar conductivity of sodium acetate. All I am taking are strong electrolyte. And I will subtract from this the molar conductivity of HCl. Is this point clear? I think you can see. Okay. I'll just write it over here because I'm not sure whether you are able to see that. See, this space is enough. See, suppose I want to find out the molar conductivity of acetic acid. I can't do that. But what I can do is, I can find out the molar conductivity of strong electrolyte, that is HCl, plus I can add to that the value of sodium acetate, CH3COONA, and from that subtract the molar conductivity of NaCl. So what am I talking? Molar, the given equation is molar conductivity of weak acid, acetic acid, should be equal to molar conductivity at infinite dilution of acetate ion and H plus ion. If I am able to get this value, my work is over. How do I get it? I have molar conductivity of HCl is what? It is molar conductivity of H plus ion and molar conductivity of Cl minus ion. Equation number 1. Molar conductivity of sodium acetate is what? Molar conductivity of acetate ion and sodium ion. And what is the third one we have? We are subtracting molar conductivity of NaCl, that will be minus, because we are subtracting, minus molar conductivity of Na plus ion minus molar conductivity of Cl minus ion. So can you see, if I add these values and subtract from NaCl the molar conductivity of strong electrolyte, this gets cancelled with this, Na gets cancelled. So what are you left with after this? You are only left with these two values which you are adding, and that is what is the answer. So this is the application of, one of the applications, I have not yet completed. This is one of the application of Kohlrausch's law, that we can find out now the molar conductivity at infinite dilution for weak electrolyte. What is the second one? The second one is the second application. We have space over here. The second application is in finding or determining the degree of dissociation. Determining the degree of dissociation and dissociation constant. That is why I taught you ionic first and dissociation constant. So alpha, the degree of dissociation will be simply, it's going to be a what do you call, alpha, the degree of dissociation is always a fraction. So what happens? It is molar ratio of molar conductivity to conductivity at infinite dilution. Now K, the dissociation constant, will be equal to what? Alpha square upon 1 minus alpha into C. So substitute, what do you get? This M whole square upon 1 minus alpha, that is molar conductivity at into C. So this will give you the, what do you call, the dissociation. For a weak acid, dissociation constant is Ka. For a weak base, dissociation constant is Kb. So this was the second application. The third application is, now I have no choice. The third application is in determining the solubility and solubility product of sparingly soluble salt. Soluble salts, they are electrolytes, but which when they dissolve will give very small amount of ions. It is clear. For example, silver chloride. If you put 1 mole of silver chloride in water, in a liter of water, only 10 raised to minus 7 moles of it dissolve, and that dissociates completely. So your silver ion concentration is 10 raised to minus 7, chloride ion concentration is 10 raised to minus 7. Now you got over here this equation, if you remember. Molar conductance is equal to 1000 into K by C. So nothing. If you will, I'll teach you how to find out the conductivity. We can find out the molar conductance. And what will you get? This C is nothing but solubility. This is the concentration. And once you get the solubility, depending on binary salt, this KSP is S square, ternary salt 4S cube, pentary salt 108 S raised to 5. So that's how we are going to find out the solubility product. So ionic teaches you solubility product. Electrochemistry teaches you how to find out the solubility using electrical conductance method and then find out the values there. Okay. So this was one bit of work of conductivity. Measurement of Measurement of conductivity. So in order to find out the conductivity K, okay, conductance and all that, first thing is we need a conductivity cell. First thing we need is conductivity cell. So in this conductivity cell, what happens is basically a beaker. It's basically a beaker in which we have put two platinum plates. I had shown you the platinum electrode, if you remember. Exactly the same thing we are talking, kept at a certain distance. Okay, and then this is properly sealed and so that it doesn't move and all that. So we can put the electrolyte over here inside this. So electrolyte is put into this, whatever we have to measure. Now you know that K, the conductivity will be 1 upon R. See, let's talk like this. 1 upon R is equal to 1 upon rho. We'll start with this. R is equal to rho into L upon A. So we'll not make a mistake. So 1 upon R is equal to 1 upon rho into A by L. Once again, so this is K. So this will be conductance G. So that will be equal to K into A by L. So your K, the conductivity, became equal to what? G, the conductance into L by A. But your G is nothing but 1 upon R, the resistance, into L by A. So I need this equation. So what happens is, what is L by A? This is your A and this is L. Now how do we find out this? So what we are doing is, we are not measuring conductivity or conductance. We are actually measuring the resistance. And this value of L by A for this conducting cell is a constant, because we measure it once, keep it steady. Okay. This is done by what we call as Wheaton's network. Wheaton bridge network. So what happens in Wheaton's bridge network is, so on one arm, what we have done is, we have connected the conductivity cell with that suitable electrolyte. And what are we going to find for that electrolyte? We are going to measure the resistance. How are we going to measure the resistance? So this is connected to a variable resistance. See, this variable resistance is actually called as post office box. You just plug one of the plugs, that much resistance comes into the circuit. Then what happens is, so this is A, B, C. Now here, from here, what happens is, we have a headphone and then this headphone is connected to a jockey. So this is X, and B and C are connected by AC current. So in your physics, maybe you'll use DC, but here in electrolytic experiment, we'll use a AC current. Why we are using a AC current? What will happen if we use DC? If we use DC, electrolysis of this will take place. Electrolysis of the electrolytic solution will take place. We don't want that to happen. When DC is used over here, use a galvanometer. When AC is used, we use a headphone. So as we go on tapping, at one point what happens? The noise on the headphone will be maximum. When the noise is maximum, that means there is no conductance. And in that case, what happens? Now AB upon BX, this is the length, is equal to AC, what resistance you got in the post office box, into XC. So what is your AB? AB is your resistance of the cell. So R, the resistance, is equal to BX into AC upon XC. So you get the resistance. Once you get the resistance, you know cell constant. This is called as what? Cell constant. You will get the conductivity. Once you get the conductivity, you know the concentration of the solution because you prepared the concentration. 1000 into K by C will give you the molar conductivity. So this is how we determine the whole story with which we just started the chapter with.